So I've started recording and now I will share the screen. Okay, so I'm guessing everyone can see my slides.
Yes, sir.
Yeah, great. Okay, so welcome to the techniques part of the local field potential module 2. As I mentioned, doing this for the first time. In the previous years, a different instructor used to teach this. So your feedback is will be needed for me to pace this properly. Okay. So if I tend to go too fast or too slow, or if something is not clear, please stop and ask. Because, as I said, I'm doing this for the first time. Okay, so first let me show you the data, the local field potential data, the biophysics of which we discussed in the last two classes. Then, as before, I'll ask some questions, and this time to build the math, we will take several classes because this is all stuff that takes at least a couple of courses worth of classes to get familiarized with. So we will be dealing with the Fourier analysis, which is a very involved and very awesome concept. It's something that is so deeply ingrained in the electrical engineering sort of curriculum that it keeps coming in various contexts. So I'll try to give you an overview of that in a few classes. Okay, so let's get going. So this is the same electrode that recorded the spike data that you played around in the first module. Okay, so the monkey looks straight at this dot. You present a couple of stimuli, one on the receptive field of the neuron, which here is shown in this red circle, which is not visible to the monkey. The monkey only sees these two great gabors, but this gabor also stimulates the brain where the microelectrode is. So here's the microelectrode. The information from the visual world goes there, and it produces these sinks and sources that we mentioned previously that leads to the local field potential. So the raw signal that I record from the microelectrode, in order for me to analyze it, I need to store it on a computer, right? So the way to do this is that I first filter it in some range, and I will tell you why this filtering is done in a few classes, and then I digitize it. So for each second, I record 2000 samples, and this is the signal that is recorded in the computer and is shared with you. You can get the LFP data from the web page, from the course web page. 1 second, I'll just be right back. Yeah, I'm back. So we'll get to this digitization and the filtering bit in a few classes, and why we filtered it before digitization will become clear then. Right now, just let's look at the data. So this was the spike data that we already looked at in the previous module. Again, so this is the raw signal. I filtered the signal at a higher frequencies above 500 hertz to 5 kilohertz, and extracted the spikes by putting a threshold and saying every time the signal goes below that level, I call it a spike. This is what this is. 76 trials, each one producing action potentials recorded like this. And if you apply that filter that I mentioned, so this is between 0.3 to 500 hertz. This type of a filter is called a Butterworth filter. We'll talk about filtering also in a later class. The output is this time series. Okay, and I've sampled it so that there are 2000 samples of the signal every second. Okay, and if I look at all of them together, there are 76 traces here, each correspond to one presentation, and it is 4096 data points per sample. So this is a matrix of 76 cross 4096. This is how the raw LFP data look like if you just plot this. This is a matrix here, electrode 1, and this matrix has size 76 cross 4096, which is being plotted here. Okay, so now you will say, okay, this is samples now. I want the x-axis as time. So there's another variable called time vals that is provided, which tells you what time corresponds to each of those 4096 samples. So if you plot time vals comma this, it will give you this plot. And you can see that after time 0, there's this negative dip, about half a millivolt. This is the presentation of the stimulus. Okay. Remember, the stimulus was presented for 400 milliseconds. So 0 to 400 is when the stimulus is presented. Why do you have a dip here? Anyone? Why do we have a dip here? This is the previous stimulus. You guys are with me, right? I'm not talking to.
Yeah.
Yeah.
No,
So remember, the stimulus is presented for 400 milliseconds and removed is blank for 600 milliseconds. So you're flashing stimuli every 400 milliseconds. But in a trial, the monkey is looking at several of these stimuli. Its overall duration is usually about 3-4 seconds. That's as long as a monkey can fixate at a dot without getting too upset and giving up. So within that 3-second, 4-second period, you flash several stimuli. So this -1 is when the previous stimulus was presented, and it's randomized. So the previous stimulus is sometimes strong, sometimes weak, sometimes oscillatory, sometimes something else. So it's not as localized as this one. This is the same stimulus at 0. That's how I am. That's how I have segmented this data. And the previous stimulus was off at -0.6. So there's some off response here, not very well observed in this. And then blank period is from -600 to 0. And after that, there is again a stimulus for 400 milliseconds. Then there's an off response, which is again not as visible. So you could just look at the mean of this, okay, the average activity, and this is called the evoked response or the evoked event related potential, or ERP. And there, this is just the average of those 76 traces. And here you can see a very nice dip here, and goes up after the off. This is the off response, and then it sort of settles back to 0. This is a very stereotypical response that you get from any type of brain signal, be it EEG, ECOG, or LFP. Okay, so I can align them together. This was the PSTH, this is the raster plot, and this is the event-related potential, ERP, or the evoked response. And you can see that whenever the stimulus came on, it excited the neurons and it generated, sinks and sources, and the LFP and the spiking activity both reflect that. Okay, so this is the signal that I'm going to look at for the next, for this entire module, the local field potential. The evoked response is just the average of these trials. Okay, so now I'm going to ask a few questions and we will develop the math to answer those questions. So first of all, as I mentioned in my previous class, that whenever a stimulus is presented, it often induces certain oscillations. In fact, there are oscillations in the local field even before a stimulus is presented. So I want to know whether there are any oscillations in the local field potential. Next, I want to know if there are some oscillations, is the power or the frequency of these oscillations, if they are present, do they change with time? Is it coming on or after the stimulus presentation, going away once the stimulus is taken off? Is it always present? Things like that. And finally, is there any relationship between the spiking activity and the local field potential? Okay, and we'll look at several ways of relating spiking and LFP. So this is the stuff that we'll do in the next, maybe 12 odd classes. So it's a lot of theory that needs to be built, but it will all be related to these questions. Okay, so let's go ahead now and talk about the analysis that is done in order to answer these questions. This takes us to the domain of Fourier analysis, which I will discuss now. So, when it comes to Fourier analysis, there is one resource which is great, and in fact, in most places that I at least have know of, is the same set of books that are referred. And in fact, it's just one guy here, Oppenheim, who has written these books. So Oppenheim and Wilsky, Signals and Systems. This is the first course that electrical engineers do all across the world. So we did this as a single course in IIT Kanpur when it is taught in the second year. And then the advanced version of this is this one, Oppenheim and Schaefer, discrete time signal processing. Okay, and I have found out recently that Oppenheim's lectures are now available at this open course where at MIT. So in a way, this is great that if you sit through about 10-15 of these lectures, just you're coming right from the source, right from Oppenheim, then you're all done. Okay, so I think the reason these books are so popular is that they very slowly, very methodically go through all the concepts that are required, and from scratch. So if you pick up signals and systems, you don't really need to know anything else. You can just have to be patient, go through the first 5 or 6 lectures, and you'll have a solid grasp of everything that we are going to discuss in this course. Okay, so this is complicated stuff. There are several variants of this Fourier analysis depending on the type of signal, and it's sort of sometimes you tend to get lost in these variations. So usually it takes a while and some reading to some thinking and all that to get hold of the concepts properly. So please take this time to do it. Okay, so at IISc there's a different course offered, a full-time course called DSP. I don't think we have a version of this here. It's an undergrad course. Well, so is this one also, but this is taken in the 3rd year, this is in the 2nd year. But as I said, the books are self-contained, and most of this I will be doing in the course, and the online courses are also available. So as far as resources are concerned, they are plentiful. So please use these resources. So also this one very awesome website, 3 Bluth 1 Brown. And they have these very intuitive and very nice YouTube videos, actually on linear algebra and on calculus and so on. So I'd recommend that also. So as far as resources are concerned, we are very well covered when we come to signals and systems. Okay, so we are going to talk about Fourier analysis. And as I mentioned, there are slightly different variants of these depending on the type of signal, whether it's continuous or discrete. And within each of these, whether the signal is periodic or not periodic. So there's a Fourier series, Fourier transform, discrete Fourier series, and discrete time Fourier transform. These two are, so I'm going to talk about this Fourier series and discrete Fourier series first, then Fourier transform DTFT. And you might be wondering why the discrete version has an extra one here. It will become clear when we get to this. So everything that we are going to get to will eventually lead us to DFT, which is the one that I run on MATLAB. So when I say fast Fourier transform, it's just a fast way of running the discrete Fourier transform. But to get to this, we will slowly and methodically uh, go over the concepts, and we'll try to also understand the differences between these slightly different ways of doing Fourier analysis, depending on the type of signal. Okay, as before, if there are any questions, please stop me and ask. This is very important because I'm doing this for the first time.
So,
Yeah.
I had a question on the earlier part.
Yeah.
Not Fourier. Um, so, in the previous slide, where you yes, why is there no spike in the previous action potential?
This is
Previous
not an action potential.
no signal. Sorry, that's a spike.
Oh, because the stimulus that was presented, so it's presented in a random way. So this might be a low contrast stimulus and a high contrast stimulus here, and different orientation stimulus next in the next one. When I extract it, it's always I'm just make sure that this stimulus is the same at 0.
I see.
So those 76 trials are extracted that way. So obviously the previous one is going to be different because they are presented in a random fashion.
Got it.
Okay. So to get to the Fourier analysis, we will first talk about continuous and discrete signals, and I will give you an intuition of why this type of analysis is very useful. So, so continuous signal is what you have in nature, right? Our brain signals are continuous, and every signal that we see in nature is, well, most of them at least are these continuous, but you often just look at discrete samples of it. This is actually important when you want to analyze it and store it and put it on YouTube, or put it on your web page so that you can download and things like that. So that's where it has to be discrete, discretized and stored. So this gives us a discrete time signal, and the representation changes once you have a continuous and they're looking at the samples of it. It's a slightly different signal. You don't have the entire thing, access to the entire signal. You have access to a finite set of samples. But if the signal is not changing too fast, turns out this is sufficient. These samples are enough for you to recreate the entire signal. So we are going to deal with these two types of signals, the continuous and discrete time signals. And we are going to essentially think of this whole process as, some modification of the signal. So there's an input signal, and I have got a system which changes this signal. What do I mean by a system? It could be a filter, which filters and removes the higher frequency components, let's say, or it could even be the brain. You could think of the brain as a system where the input that is coming in is the visual stimulus or what you are hearing, and the output could be the behavior of the animal, or if you are recording the brain signal using electrodes, this output could be the brain signal, the LFP that I'm looking at. Okay, and if I present different types of stimuli and look at the response, I understand something about the system. Okay, so this system is this abstract thing that we are trying to understand, and it takes some inputs and produces some outputs. And if I'm very clever, by looking at this input output mapping, I can figure out how the system works. So even if I present a input that I have not presented before, I can sort of make some predictions about how the output is going to look like. Okay, so this is the main formulation, and we will see that if the system has some nice properties, then it's very easy for me to predict the output for any type of input. Okay, it's not always possible, but in some cases it is possible. And these kind of systems are called, so the systems have these properties. So this one property, which is called time invariance, which is very useful, and another property which is called linearity. So systems that are linear and time invariant are called linear time invariant systems, or LTI systems. And these classes of signals are, these classes of systems are of a lot of value, because these classes of systems can be described and analyzed very well. Not most of the signals like our brain, they are not LTI systems. Okay, but so you can make a good approximation. Many systems, even though they are not LTI to begin with, can be approximated very well with LTI systems, and therefore, it's of a lot of value for us to understand the LTI systems. So let's try to understand what time invariance means. So conceptually, it's very easy. System is time invariant if the behavior and characteristics of the system are fixed over time, which means that if an input X produces an input Y, if I have a delayed version of the input, the output will be the same, it will just be delayed by the same amount. Okay, this is what it means to have a time invariant system. So let's take an example. Suppose Yt is X of 2t. So here I am showing you X of t. Let's think about this. So suppose X of t is a rectangular pulse like this. So it's 0 everywhere, but between -2 and 2 it takes a value 1 and becomes 0 again. If I want to plot Yt, can anyone tell me what Yt will look like? This is where chalk and actual, oh, I want to show you this. Wait. I will just come here and I will actually use a Jamboard here. So who can tell me what xt is going to look like? Oh, sorry, xt I know. This is xt -2 to t 2. Yt is x of 2t. So how does it look like?
Stretching in one direction.
Yeah. Twice
Like this?
Yeah.
Sure, everyone? Well, so it's either this, so let's say this is 1, or maybe it gets squished. -1 to 1. It's one of these two. Which one is it?
It gets squished.
Squeezed.
It'll get squished.
Okay. Who thinks it's going to get stretched? Nobody's answering. Who thinks it's going to get squished? Squished. Just say yes.
Yes.
Okay.
Yes.
So yeah, it's not as much fun to do this virtually, but so the squish people have it, and that's the right answer. Okay, and just it's not very hard to see because when t is -1, then x of 2t is just x of -2, which is 1, right? So it becomes 1 here, and so when when t is equal to 2, then x of 2t is just x of 4, but x of 4 is 0, right? So y of 2 is going to be 0 because y of 2 is equal to x at 4, which is 0. So y of 2 can't be 1. When is y going to be 1? When x is between when t is between -1 and 1, because then 2t is between -2 and 2, that is where x is 1. So it actually gets squished. Okay, so this is yt, not this. This is not right. X of t by 2 would have stretched it by a factor of 2. Because when t is 4, t by 2 is 2, and then the whole thing remains 1 between -4 and 4. This is actually equal to x of t by 2. This is by t. equal to x of 2t. It's a little counterintuitive because you think you multiply, so you expect it to expand, but it's actually the other way around. Okay, so let's go back to our example. So y of t is x of 2t. So I want to plot all of these. y1t, x of 1 of, sorry, so this is x1 here. So y1t is what I plotted. And I'm going to plot y2 of t and y1 of t minus 2. Okay. So actually, let me just show this to you. So x1t gives you y1t, which is, as I mentioned, is a squished version of this. y1t is just x1 of 2t. Now I have got a shifted version of x1, which is x2. So x1 got shifted by 2 units. So this was here, shifted version is this. y2t, which is x2 of 2t, is just going to be a squished version of this signal. Correct? Let me know if if I need to repeat anything. So this is y2 of t, which is the squished version of x2t, but the shifted version of y1t, which is y1t minus 2, is this, and these two are different. Which means if I shift the signal and look at the output of that, it is not the shifted version of the original signal. The shifted version of the original signal is this, and this is the output of the shifted version of the output. Okay, so this property doesn't hold. When x1t produces an output, so my signal here produced this output, then I looked at xt minus 2, that's this, and the shifted output is that. But yt minus 2 is this. It's the shifted version of that, and these two are not the same. So this equation, this system, a system that squishes the time by a factor of 2, is not a time invariant system. Okay, everyone happy with this? So I'm just giving you an example of a system which is not time invariant. But if I had something like, yt is equal to xt plus 5 or 2 times xt, they are all time invariant systems. There it doesn't matter. Okay, so I'm just showing you an example of a system that is not time invariant. These systems are not of much use. I would rather have something that is time invariant because those are easier to analyze. Okay, so this is time invariance. Everybody okay with this? So then I will talk about the second property, which is linearity. This one is, I guess, a little bit easier to understand. If I give you a signal x and the output is y, and an input x2 whose output is y2, then if I give you an input x1 plus x2, then the output is going to be y1 plus y2. These are linear systems. Similarly, if I give you a scaled version of the input, I get the same scaled version of the output, where a is any complex constant. So you can actually combine it and say that if I give you a scaled and superimposed inputs, ax1 plus abx2, my output is going to be a y1 plus b y2, where y1 and y2 are the outputs of x1 and x2 respectively. Okay, so here are a couple of examples of linearity. So if, well, let's just do this. A txt is linear and x square 2 is not linear. So these are examples in, O and W is Oppenheim and Wilsky. So I really recommend getting this book. It's an awesome book, and you should just, you know, go through these step by step. Make a lot of sense. So let me just do this here. So if I've got yt is equal to txt, sorry, txt, then y1t is tx1t, y2t is tx2t. And if my input is ax1t plus bx2t, it's easy to see that. So if this is my x3, then y3 is just t x3t, which is t at x1t plus bt x2t, which is just ay1 plus by2. Right, where y1 by definition is this and that. So this is a linear system. So this is linear. Likewise, it's easy to see that if I've got a squaring operation, so if x1 produces output y1, then y1 is x1 square t, and I've got another input y2, x2, that then y2 is x2 square t. But if I give ax1 plus bx2 as the input, then y3 is x3 square, which is a1 x square x1 plus a square b square x2 square plus cross terms here, which is not you know, your a by 1 plus b by 2. Okay, so it's easy to see that this is not linear. This system, so these are properties of the system. So this is a case where the system is not linear. Okay, so we talk about linear and time invariant systems in a lot of detail. It may seem very restrictive to you that, hey, why are we only dealing with you know, such a restrictive class of signals? But turns out many physical processes actually possess these properties, and it can be modeled as LTI systems, and they can be analyzed in a lot of detail. And there are lots of powerful tools that are used to then characterize these systems, which is why we use the LTI systems so well. So when I was a graduate student, during my compre time, this was many years ago, my advisor was a big fan of linear systems. So that day he started asking, during compre, he asked me to prepare for some other stuff that he never asked. And then he asked these questions: why do you think linear systems are so popular? And he thought the reason was that many of the basic laws of physics are linear, which is where this linearity comes in. And then he asked, why is the exponential system so popular? And the answer is that the exponentials are actually solutions of linear systems, which is why you see exponentials everywhere. Why is the Fourier transform so popular? Because the basis functions are complex exponentials. Why is the maximum likelihood estimate so popular? So he's asked these set of questions. It was a very hard compre for me because I was thinking those things through, at the time. But actually you can track down a lot of how the math is in the world down to linearity. It's amazing that once you start from this, that the basic laws of physics are linear, you can explain why Fourier transform is so popular, why estimation is done a particular way, why exponentials are so popular, and things like that. It all boils down to linearity. Okay, so even though it seems like a restrictive class of systems, it's actually not as restrictive. It's very useful to model various systems as LTI systems, even though if they are not. And we will certainly do that for rest of this class. Now, when you have a LTI system, turns out if you give a particular input and you know its output, then if I can decompose any input as a sum of those basic inputs, I can construct the output very easily, because the output is just a scaled and shifted sequence of that basic signal. Okay, so that's the basic idea that I'm going to get into. And I'm going to start with this very basic signal called an impulse function. And we will see how my understanding of how an LTI system responds to an impulse function can be then used to find out how it would respond to any input. Okay, so input impulse function is the easier of the two. So I will start with that. And then we will see where complex exponentials come in. And this will lead us to the understanding of the Fourier analysis. So we will get to that maybe in the next class. Today I'm going to talk about how a LTI system responds to an impulse function. Okay, so here's what an impulse function looks like. This is right here, the first plot. It's a function that is 0 everywhere except at 0, where it takes a value of 1. So this is a discrete time impulse function. It's an easier to understand than a continuous version of this. So it's 0 for n not equal to 0, and at n equal to 0, it takes a value 1. That's the impulse function. And we also talk about what is called a unit function, which is 0 everywhere for n less than 0, and then it becomes 1 everywhere. Okay, it's easy to see that the delta function is also called a impulse function, also called a delta function. The delta function is just un minus 1. Un minus 1 is the same signal, just shifted right to one side. When you subtract it, all these ones get subtracted, and you will be just left with 1 at 0, which is your delta function. See that? So this is the un minus 1. Likewise, if you take the delta functions and do this summation, you will end up getting the unit function. This might be a little bit tricky for you to see, but just convince yourself of this. What am I doing? Here, this n is the variable. Okay, so every delta m is a function which is like this. There's a delta function at 0. So I'm looking at the summation of interval. This is n here. And if n is less than 0, then I catch nothing. I don't catch this guy. So any summation like this where n is less than 0 is just 0. But when n is greater than 0, then the summation will catch this and un will become, the summation will become 1. So this whole thing here is 0 for n less than 0 and becomes 1 for n greater than 0. So it's nothing but my unit function. Okay, please take a moment to convince yourself of this. And if there are questions, I will repeat this again. The reason I want you to see this is because the delta function seems to be like the derivative of the unit function, and the unit function seems to be the integral of the delta function. Here you are not seeing integrals and derivatives because it's discrete, but that's exactly how it will boil down to when I get to the continuous version of the same thing, which is harder to interpret. So is everybody okay with this, or do I need to repeat this? The delta function being here the subtraction of the unit function, and the unit function as an infinite sum of delta functions with from minus infinity to this number n. Is this okay? Okay, I'll take silence as yes. Okay, so usually if in class I look at faces, and if everybody is looking here and there and looking confused, I repeat. I can't do that right now. So if you have questions, please ask. Otherwise, I will move. You'll have to be more proactive here. Can't look at your faces. Yeah, there was a question.
Sir, can you explain the un is equal to summation of delta m? I'm a bit lost.
Yeah,
in
so
that
that's what's shown here. I'm looking at the interval of summation minus infinity to n, and if n is less than 0, then I don't have this one here, so the summation is just 0. So this thing for n less than 0 is just 0. And when the interval of summation is greater than 0, then I will catch this. So the summation will have will be 1. That's it. So
basically we're just shifting the delta for the basically we're just shifting the delta and adding them for un, right?
You're not shifting the delta, you're actually looking at the samples of the delta function, and so delta m is this whole thing, and here you can think of it, you're adding the samples from minus infinity to some number. If that number is less than 0, then I am just catching the zeros. So the summation of this is just 0. Interval of summation for n less than 0 is just 0. The interval of summation when this is more than 0 is 1. Then when I'm adding this, I get 1. That's what it is. Okay, I'm not shifting the samples. This is the delta function, and I'm summing the values from minus infinity to n, where this n could be either less than 0 or greater than 0. Okay? That's fine?
Yes.
Okay, so now let's get to the more complicated version of the same thing, because it leads to a function which is very popular, but actually is very hard to understand. It's not something that you will see in real life. This is the continuous time impulse function. So how do I see this? I first look at the continuous time unit function, which is very easy to understand. It's a function that was 0 before time equal to 0, and then it became 1. This is easy. But now think of the impulse function as the derivative of the unit function, just as you were looking at the difference in the discrete domain. Now how it should look like? So let's think of this, my unit function, as an approximation where it doesn't jump to 1 immediately, it jumps to 1 over some little interval delta. Okay, so over an interval it became 1 and then it stayed 1. Okay, this is easier to understand, what is the derivative of this function? Well, the derivative is always is 0 here and is 0 outside after delta as well, because it's not changing, so the derivative is 0. Between 0 and delta, it has the value 1 over delta. Okay, that's how fast it's changing. So the derivative looks like this. And notice that the product, the area under this curve is always 1. Okay, everybody happy with this? This is the derivative of u delta t, where u delta is like my delta function, unit function, but it slowly changes between 0 and delta. What happens when delta becomes close to 0? This thing will shrink and the output here is going to expand, always preserving the area to be 1. And as delta approaches 0, I get what is called the continuous time impulse function, and I denote it as a vertical arrow like this with a little this thing shows it's actually infinitely long. However, it's also infinitely thin, such that the area is always 1. The impulse function is a derivative of the unit function. This is how you indicate it. You would say, why I am talking about a function which I have never seen in real life? And this is because even though you won't see this in real life, this is such a useful function that the math that we'll do becomes very easy to be expressed in terms of a delta function. Okay, so a delta function has 0, it's only sitting at 0, so it is infinitely thin, it's infinitely long, but it has unit area. If you integrate it, you get ut. Again, it's a delta function sitting at there. If you integrate this delta function over an integral that doesn't include it, so interval of integration is this, you get nothing. But as soon as you integrate it over an interval that includes the delta function, the integral of this is 1. So this whole thing is just ut. It's 0 for t less than 0, 1 for t greater than 0. This part is a little bit confusing, but it's exactly the same logic that I had given you here. So the integral delta functions and unit functions are integrals and derivatives of each other, as shown here. And it's true both for continuous domain, which is harder to understand, as well as the discrete domain, which is relatively easier to understand. Okay. So why do I care about impulse functions? So two reasons. Yes.
Sir, so if correct me if I'm wrong, but like if whatever I understood, so till now what I understood is that we cannot get a signal until unless the time interval which we are taking is greater than 0. So means like
the integral will be, yeah. So if the interval of integration doesn't include the delta function, then it's all 0.
Okay.
But if the integral includes the delta function, no matter where it is,
okay.
it's going to be, the integral is going to be 1.
Okay.
So ut is going to be 1 for all values of t greater than 0, and it's going to be 0 for all values of t less than 0. So it's the delta function.
Okay. So how means I don't what I'm thinking is how do we define like means how we define a 0 here, means like what
0 is 0.
No, I don't know, I'm not able to formulate the question itself, but
no, so see, this is a very deep rooted question. Okay, so mathematicians over centuries have wondered about what it means to be a discontinuous function, and mathematically this is the work of like scores of mathematicians who have laid it down to such a precise level that you'd be amazed. But to have a clear answer of these questions, you have to understand the number line, this is all real analysis, so, there are several courses worth of stuff where you talk about what it means to have a hole in the number line. Like, for example, rationals are not dense enough. So these questions actually are quite profound, but real numbers are dense. They span the entire real line so that it exactly means what it means to approach zero and what it means to, be greater or less. This is profound stuff. Okay, but the math here holds up, but it's wasn't always like that. Now you can create signals. Let's say if I have a signal which is 1 for all rational numbers and 0 for all irrational numbers. Okay, so now it's a tricky question. Can you take the integral of that?
Yeah.
Anyone? Just as let me just ask this just for fun. Suppose I have got a signal which is 1 for all rational numbers and 0 for all irrational numbers. Can I integrate that function?
Yes.
Yes. What is the integral?
0.
Why?
Because the measure of rational numbers is 0.
Okay. What is measure? What do you mean by measure?
Measure of set of rational numbers. Okay. You can say measure is a length.
Okay.
Of that, and integration is just value into length of set. You can think about that.
Okay.
Like that. And if the length of set is 0, then the
very
integration
good.
is 0.
Very good. So it turns out the answer is correct. You can't take what you guys are seeing here is a type of integration called Riemann integral. So it doesn't have a Riemann integral. What's your name? The fellow who talked about the measure?
Chandrakant.
Chandrakant. Okay. Yeah. So Chandrakant. So you're talking about the Lebesgue measure.
Yes, sir.
Okay. So there are more complex ways of interpreting all these questions. Okay. And everyone should have these questions. What it means to have something sitting at 0 and not a little bit here and there. Mathematicians have pondered and actually done it to such a beautiful level that it is mind-blowingly amazing. Even when we started with Fourier analysis, Fourier himself did it to some level, but then there was another guy, Dirichlet, who actually made it very precise. When you can take Fourier analysis, and in signals and systems, some of that is covered, not in a lot of detail, but they keep telling you about where to get this, because this can get very detailed. Okay, so even in this case, the integral that you just mentioned, here we are talking about a simpler form of integration. Turns out the number of rationals are countable, but irrationals are uncountable. It's a much larger infinity. So when you talk about the weight of this, irrationals are much more weighty than rationals. So even if you put a 1 on each rational, the integral, the Lebesgue measure is actually 0. Okay, this is fun stuff that I'm telling you, because I also was very fascinated with all of this when I was, your age. And I took courses on real analysis, and, it's really beautiful. The guys who first did this, like Cantor and, those are people who fought against the entire system. And they died in mental asylums and, committed suicide because no one else would understand what the hell those guys were talking about. And then decades later, people understood this is the shoulders of the giants who did fields like measure, this real analysis and, complex analysis, looking at real numbers, the different levels of infinities that are involved with different types of sets, how you can integrate these functions. But today, as we look back, every question that you can think of, maybe not at a research level, but these kind of questions, these are important questions. We have answers thanks to these generations of mathematicians who have made the things very precise. Okay, so don't be afraid to ask these questions. Okay, so and think about this because you will be seeing things like delta functions that may not mean look odd, and you might be wondering. It's completely okay to bring these questions up. And if I can't answer those, I will refer to people who can, or the text which can answer this. Fortunately, we won't be able to answer a lot of these questions. Okay, that's the way it is, because in like 5 odd classes, I'll be trying to cover something that is covered in like 3-4 courses worth of stuff. But um, you know, please ask these questions to yourself and be amazed, and ponder over this. This is how you become you know good scientists. Okay, so I'll stop here. Run out of time. I'll maybe just tell one thing. You can just ponder over this. An impulse function is actually something that samples the signal. If I multiply a signal with an impulse function, it's the same as the value of that signal at that value. This is easy to see because the delta function is 0 everywhere else. So at 0, x0 delta 0 is just x0, which is x0 delta n, because if for any other value of n, it is this. So you can think of a delta function that samples the signal, and interestingly enough, this also holds in the continuous case. So I'll leave you with this. Okay, the stuff that I'm going to follow in the next few classes is different from the way I have done it in the past. And this is exactly how all electrical engineers learn it. And this is the mathematical way, which is very different from this intuitive signal, look at the signal type of wave that we have followed in the previous module. And the reason is that all this math has to come in an abstract way before we get to DFT, and only then we'll be able to relate it to the actual signal that we have at hand. So it's please read this stuff. Okay, the resources are all there. Please take the time and read it, and be more interactive in class. And that's how we will cover this slightly different part. Okay. All right. So I'll stop for today. If there are any questions, I'll take them. Otherwise, we'll again meet on Monday. Okay. So looks like today there are no questions. So I will stop sharing. I'll stop recording as well.